Welcome to the Space Telescope Public Lecture Series. Tonight's talk, The Pillars of Creation, Multi-Wavelength Explorations in 3D by Frank Summers of the Space Telescope Science Institute. I am Frank Summers of the Space Telescope Science Institute, and I'll be your host as well tonight. As always, I want to thank our wonderful tech team, Thomas Marufu and Grant Justice, for bringing you this webcast. Our upcoming talks on August 6, 2024, Year 2 in Review, Groundbreaking Science Discoveries by the James Webb Space Telescope. This will be by Macarena Garcia-Marin, also of the Space Telescope Science Institute. And in September, we will have a talk on the Roman Space Telescope by Ori Fox, also here of STSCI. Our October 1st talk, well, that's to be decided because I haven't roped somebody in to give that talk just yet, but I will. And when I do have that, it will be posted on our website, www.stsci.edu/public-lectures. There you will find all the information you need. In the lower left, you will find links to our webcasts, both on our webcasting site that we host at STSCI, as well as on our YouTube playlist. In the lower right, you can see how you can sign up for our emails. You get probably about 2 or 3 emails a month, very low, so not going to clutter your inbox. Also on that website, you will find our list of our upcoming lectures, and this is where the October lecture will be posted when I have it. If you click on each lecture, you will get the information about it, the details of the presentation, as well as, after it's recorded, links to the STSCI webcast and its link on YouTube. For emails, as I said, sign up at the website. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. You'll get, if you subscribe there, you will get the new video notices and reminders of live events. Also, if you have comments or questions for speakers, you can send them to the email address publiclecture@stsci.edu. You can also follow our social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, as well as for our Institute. We have social media channels on Facebook, on X, on YouTube, and on Instagram. Now, at this point, I usually do my news from the universe. Unfortunately, as I was preparing my talk this month, I didn't have time to create a news from the universe segment, so it will return next month. So we'll just go directly to my talk, Pillars of Creation, Multi-Wavelength Explorations in 3D. So for those of you who haven't been regular watchers, I have been at the Space Telescope Science Institute for 23 years. I've been hosting the Space Telescope Public Lecture Series for 22 of those years. And I am an astronomer in the Office of Public Outreach. So I help out on all the various outreach avenues for Hubble and Webb through news products, through websites, through educational activities. And what I've come to specialize in is doing visualizations of the universe. My academic background is that I got my PhD at the University of California, Berkeley. I did postdocs at Princeton and Columbia University before turning my life into doing public outreach, moving off the research track and doing public outreach, where I was at the American Museum of Natural History in New York. Neil Tyson, Steve Soder, and I were the 3 curators that built the Rose Center for Earth and Space and the New Hayden Planetarium in the year 2000. After that, I came to Space Telescope Science Institute. As I said, I've been here ever since. So that's a little bit about me, and here's my talk. So the Pillars of Creation is one of the most iconic images in astronomy. It captured the public's imagination. And here are the Hubble image and the Webb image. And in doing visualizations over these past few decades, I've wanted to do the pillars of creation, but I didn't want to do them until I felt we could do it right. And because this is a very complex image, there's a very lot going on in here. We wanted to express all of the scientific ideas, and we wanted to do it right in a full three-dimensional volumetric way. But before we get there, and I show you the visualization at the end, let's start with the big picture view. Let's pull back and take a look at the Milky Way and get down to and work our way down to the pillars of creation. So this is a Milky Way galaxy simulation. Why a simulation? Because, well, we can't look at the Milky Way galaxy from above because we're inside it. So on the left is the face-on view of this simulation, and on the right is the edge-on view. And I'm going to spin that face-on view, all right? And you're going to see it spin around, all right? And so here's another face-on view, and then you get that edge-on view. Now, of course, we are inside the Milky Way. It's got a pancake-like disk, okay? We're inside that disk, so all we get is that edge-on view. So when we look at the night sky, this is what we see of our Milky Way galaxy. And you can see there are stars there, but there's also a lot of black dust, these dust lanes that obscure some of our lines of sight to seeing the stars in the Milky Way. If we want to see just the stars, we don't use visible light. We can go to near-infrared light. This is the 2MASS survey, the 2-micron all-skies survey. And you can see that there's still a little bit of dust there, that brown stuff. But mostly what you can see are the stars that stretch out, and you can see that thin disk of stars, as well as a bulge of stars in the center. Okay, you can see the stars. Now, if you want to see the dust, you actually will go to far infrared light, and this is observations from the Planck satellite. And here is the dust. Again, you get that wonderful thin plane along the plane of our galaxy. Plus, you get a lot of dust that's up above the plane, and that's actually dust that's nearby us. Our sun is actually located just below the plane, and so dust that's nearby actually looks like it's up above the galactic plane, and it is from our perspective. All right, and then a special component of the dust can be seen in microwave light. And there are special frequencies that you can look at in microwave light to see carbon monoxide emission. Right? Why carbon monoxide emission? Because it's an indicator of where the molecular clouds are, the cold, dense dust. And those molecular clouds are very important because those are where stars can form. All right, you want the dust clouds to be cold so they can collapse, gravity can pull them together to form those stars. If the clouds are warm, well, thermal pressure supports against the gravitational collapse, and you can't get star formation. So you need cold, dense dust clouds in order to be able to gravitationally collapse and form stars. If you want to see where the stars have already formed, you look in the light of ionized hydrogen. We call this hydrogen alpha, all right? And it's a transition within the atom of hydrogen that radiates at about 10,000 degrees. So you're looking at gas here that's about 10,000 degrees. And so when you form stars, they actually heat the gas around them and they can glow at this hydrogen alpha line. And you can see that they are, again, spread across the disk. Of course, you got some up and below. And you can also see that they have a number of circular features to them, okay? Because if you've got a cluster of stars, it radiates uniformly, and you can get what astronomers might call a Stromgren sphere, a sphere of this ionized gas. All right? So these are the components of our Milky Way. You can see the visible light up there, but we've got the stars, we've got the gas, and we've got the dust. And what we're leading to here is discussions of star formation in the pillars of creation. And I want to show you how the stars and the dust and the gas all interact together in telling the story. So let's take a look at some of those star-forming regions. This is the plane of our Milky Way, and I want to show you how small these star-forming regions are on this scale. So let's zoom in, and you can see this red here, that is hydrogen alpha emission, and we're going into the constellation of Orion, and below those three stars of the belt is Orion's sword, and the middle star of Orion's sword is not a star, it is the Orion Nebula. And here you can see the Orion Nebula, and it's got that sort of roundish shape because it's being heated by stars in the core. Let's go to the Hubble image of the Orion Nebula, and you can see it's beautiful. It's really got a wonderful flowing structure. It's about 10 light years across. And if I zoom in, you can see the four stars of what's called the trapezium. These are the four trapezium stars that are the most massive stars and therefore the brightest stars, and really the only stars that are emitting significant high energy radiation that can ionize it. So those four stars are heating up and ionizing this entire region. That's one of the important things to understand. It doesn't take a huge cluster of stars to heat a star-forming region. Just a few very massive stars does it. Here's another star-forming region. This is called the GUM-29 Nebula. And again, this red light here is from hydrogen alpha. So this is the warm gas. And if we zoom in and use the Hubble image, you can see here this large cluster of stars called Westerlund 2. So it's the star cluster Westerlund 2 within the GUM-29 Nebula. And these stars are irradiating and heating it. But you can also see that on the right-hand side, they've actually blown away all the gas and dust on the right-hand side. So they've actually evacuated out, and it's only left on the left-hand side. But you'll also notice on the left-hand side some pillars, right? The energy from the stars eats away the gas. It actually irradiates and eats it away. And also, strong stellar winds from these stars blow away the low-density gas. So where you have a high-density clump, it will resist that erosion and actually create a streamline behind it that forms pillars like these. And here you can see you've got several pillars here in GUM-29. Now, these pillars are not that, are pretty common, right? They're not rare. Some people think, oh, the pillars of creation, that they're special because they're rare. No, that's not true. Here's another nebula, NGC 602, where you can see this bright cluster of stars has eaten out this big cavity. A lot of erosion has happened, but along the edges of this cavity, what do we see? Again, we see pillars. And where do those pillars point? They point back towards the stars that created them. So that we have in star-forming regions, the stars forming from these dense dust clouds and then eating away the gas and dust of those clouds and forming these pillars. This takes us to the Eagle Nebula. And here is a nice image of the Eagle Nebula from a ground-based observer, William Osling. And what you're supposed to see is the shape of an eagle with its wings. And so I found an image online. Okay, yeah, that's sort of thing. I mean, this is one of the few nebulae where I can say, yeah, I can sort of see the eagle in the Eagle Nebula. There are some others that have other names, and I'm hard-pressed to be able to imagine them. But this one I can kind of imagine. All right, and you can see that the Eagle Nebula isn't evacuated like NGC 602. The star cluster hasn't eaten it away. So maybe you might say, well, why would there be pillars if you haven't eaten away a lot of the dust? Well, let's zoom in, all right? And here is that star cluster. And here are the pillars of creation in the center. And on the left side, there's another pillar that we call the stellar spire. When we observed it with Hubble and released it, I think it was around 2005, 2006 that we released that image, okay? And again, the pillars of creation and the stellar spire both point towards this cluster of stars. But you may also look at this and say, well, wait a minute, that's not the pillars of creation I know and love. It doesn't jump out against the background. What's going on here? Well, here you're looking at it in visible light plus some hydrogen alpha, all right? If you use different filters, you get this view. And this view is more like what you're used to in seeing the pillars of creation from Hubble. All right, so this is a view where you look at the particular emissions from sulfur and portray them in red, hydrogen and portray them in green, and oxygen and portray them in blue. And astronomers do this choice of filters to be able to probe the science that's going on in these star-forming regions. These are three common filters. And based upon that original Hubble image, this has become the SHO color palette for looking at star-forming regions. And you'll see a lot of images online using this SHO color palette. Another way to explore it is, of course, to use non-visible wavelengths. And here is the near-infrared view of the Eagle Nebula. And again, you can see the pillars of creation there and the stellar spire. This brings up in the red dust that we see in near-infrared light. You can also see the stars in the bluish green here. All right, and if I go back to the visible, all right, you see plenty of stars, but you see more in near-infrared light because it picks up the low-mass stars, the most numerous stars, all right? And if you want to see just the dusk, again, you can go to the far infrared light, and this is a wonderfully colorful image from the Herschel Space Telescope. And again, you see the pillars of creation and the stellar spire and all the structure in dust because they are dust clouds. And you see that they are interconnected, that they're sort of a skeleton to the nebula that you can see in the dust that, of course, you can't see easily in visible light. Now, one thing that surprised me as I started work on this project was to find out that you could see the stars by adding X-ray light. So this is a combination of the far infrared light from Herschel and the X-ray light from the XMM satellite. And it turns out that protostars, stars that are in formation, go through a stage in which they emit X-rays, all right, and significant X-rays. And you can see that these are stars of that central cluster that are protostars going through that stage, and you can see a lot of protostars there. Matter of fact, the Chandra X-ray Observatory detected over 1,700 individual sources inside the Eagle Nebula, and about 1,100 of them were identified as protostars within this cluster. They were even able to correlate some of those protostars with regions within the pillars of creation themselves. And I'll talk about that in just a bit. All right, so finally, with that intro, we get down to the pillars of creation. And this is the image that started it all. This was Hubble's 1995 image of the pillars in the Eagle Nebula. And it's dramatic because it has these dark dust pillars and they're outlined in this glow, all right? And it's got glow coming off the top, this bright yellow gas streaming away. In photography, you call this sort of rim lighting, okay? That makes them stand out and pulls them away from the background, all right? And this is what captured the public imagination. I mean, you got to remember in the early 90s, we had the flaw in Hubble's mirror that needed to be corrected. And so from 1990 to 1993, Hubble was doing science, but not all the science it was intended to do. And then we put on this new instrument, Wide Field Planetary Camera 2, which took this image, which corrected for the flaw in the mirror, and was able to get fully clear images. And this is one of the watershed moments where the public said, wow, astronomers can produce some really great images of the universe, and Hubble started to become a household name. All right. But this, as I said, was with Wide Field Planetary Camera 2, taken, wow, almost 30 years ago now. So we've had servicing missions to Hubble. We put in new instruments, and in 2009, we put on Wide Field Camera 3, and in 2015, we got this image of the pillars of creation. This is higher resolution than the previous image, and it covers a much greater field. There's a lot of detail to study, and it still has that same ethereal beauty where you can really go in details, and I will go in details to show you all of this. Also, on the Wide Field Camera 3, we have an infrared mode. So we took not only the visible light, but we also took the near infrared with Hubble. And that's quite the change. All right, this is visible. This is near infrared. Oh my gosh, look at all the stars. Well, the infrared light is longer wavelength. So it actually penetrates through the gas of the nebula and sees all these background stars. All right, they are there. They're just not visible because of the background gases glowing. And so, boom, you get to see them here. It also penetrates through some of the dust of the pillars, and we'll explore that in detail in a minute. So with that as a precursor, the James Webb Space Telescope, shortly within the first year or so of after launch, they took this image of the pillars of creation. This is a near infrared image as well, but it goes further into the infrared. Hubble only goes up to about 2 microns. The Webb's near infrared camera goes all the way up to 5 microns. So while the pillars are dark in Hubble's near infrared, they actually glow in Webb's near infrared because Webb goes to longer wavelengths where the dust emission picks up some of that dust emission. It still has all the amazing number of stars in the background. Webb also has a mid-infrared instrument that goes beyond from 5 microns up to about 20 microns. And we also took an image with that, and we got this. And this one just feels very ghostly because as you go to the mid-infrared, you're losing almost all the stars, but you are seeing that dust emission. And so you're seeing the emission from the dust of the pillars. And this is just an amazing and cool feel to it. So these are the 5 images that we're going to discuss, okay? Hubble 1995, Hubble 2015, Hubble 2015 infrared, Webb near infrared, and Webb mid infrared. But they are, while they cover pretty much the same area, they are actually of quite different resolution. So this image shows you each image at the same pixel scale, right? So there's a 1-for-1 pixel comparison. And you can see that we've got the most pixels in the Webb near infrared and in the Hubble 2015 visible. Webb is about 1.5 times the resolution of Hubble. So there are 1.5 times as many pixels per area on the sky for Webb versus Hubble. Both of them have many more pixels than the Hubble near infrared or the Webb mid infrared, or the smallest one being the Wide Field Planetary Camera Hubble image from 1995. So you'll understand if a lot of my comparisons tonight will be between the Hubble visible from 2015 and the Webb near infrared, because those are our 2 high resolution images for us to look at. Okay, so let's start by looking at density and transparency. I mean, that doesn't sound very exciting, but actually it really is. It's exciting. Okay, so you look at this Hubble pillar and you say to yourself, that looks like a solid pillar, okay? I know that I looked at it and was like, oh yeah, it looks like a solid pillar. But you recognize how these pillars form, that the high energy radiation streams down from these stars, blows away the low density gas. It hits the top of the pillar, which is obviously got to be a dense knot at the top. But it doesn't necessarily mean that the rest of the pillar has to be dense. Okay? So we can't tell that easily from the Hubble image, but if you go to longer wavelengths, in the infrared, we should be able to tell. So let's start with the longest wavelength, the mid-infrared from Webb. And here you can see that the dark regions in the mid-infrared, okay, show you those are the dense things. So there is a nice dense knot at the top. And then along the right side, you see some density structure. But the central part of it is actually kind of ghostly. All right, it's just this light, wispy emission. Can't quite tell easily how dense it is. It's actually not very dense. So let's take a look at the Webb near infrared. Okay, and when we see the same thing, a nice dense top, density along the right side, and less density in the center. But if we go to the Hubble near infrared, which doesn't have any of that dust emission at longer wavelengths of the near infrared, you actually see, and has so many stars in the background, you see the stars coming through, and you get this, I don't know, sort of like a spider shape, like you got the spider body at the top, okay, and then you got all these legs, tendrils streaming down. Yeah, that pillar is not very, it's not a solid pillar, okay? And if you look back at the Hubble image, you can start to see that, well, maybe some of this gas stuff here in the center that looks like just wispy gas in front of a dark solid pillar isn't really as solid as it looks in this Hubble image. And you can sort of see, once you've seen the infrared views, you can sort of see in the visible light views, here's how I should be interpreting it. And this is the value of having multiple wavelengths and, frankly, multiple telescopes to extend across a larger range of wavelengths to help you understand the visible light image by looking at these infrared and vice versa. We can also play this game looking at the right pillar. We call this pillar 3, or actually, my team, we called it the dog pillar. Okay, I don't know if you see this, but it looks sort of like a terrier with its front paws lifted and its tail sort of sticking out there down, and its back paws down there, and its head up. Okay, we refer to it as the dog pillar. Okay, and so you can see in Hubble it's very dark and it looks very dense. Okay, actually, when you go to the Hubble near infrared, it stays really dark, and it feels really dense. And so this one feels like it is much more solid. Well, not quite, because you go to the Webb near infrared, and it starts to get a little less solid feeling, and you move to the Webb mid-infrared, and yes, there are a couple really solid places. There's sort of a solid backbone going from the head to the tail of the dog, and a little bit across the front paws, but there's a lot of that wispy stuff that we learned earlier represents low density material, okay? So understanding that these pillars, that all will have these dense tops to them, but the structure within them needs some examination to understand them. All right. The other really cool feature about these things are these ionized gas outflows. All right. So this is what produces all this wonderful rim lighting, this beautiful lighting. All right. So here is the top of the left pillar, as seen by Hubble. And what I'm talking about is all these striations moving off away from the pillar here. Okay. And what's happening here is the high energy radiation from those three bright stars that I haven't actually told you that there are three bright stars in the Eagle Nebula, okay? We talked about Orion needed 4 stars to ionize that region. Well, the Eagle Nebula, there are 3 main stars, okay? So the light from those 3 stars hits the dust. It ionizes the dust, and then the dust flows away, okay? We call this an ionization front or a photoevaporation front, okay? That the light ionizes it, and that warm gas then streams away, and you get these beautiful streamers here. And you can see it not just in the Hubble image, but those same streamers, as a matter of fact, the same patterns of streamers also are here in the Webb near infrared. All right, and if I blink back and forth, you can see another really important feature. You say, hey, wait a minute, Frank, you didn't align these images right. And I say, no, I aligned them right. Look at those stars, okay? The stars are all in the same spot, but the top of the pillar is lower in Webb because you're looking at near infrared. You're looking at cooler dust, okay? Dust that's emitting at a cooler temperature, okay? And so if Hubble is looking at sort of the surface of the dust, that would be where it is hotter, warmer, okay? Then you have to go below the depth of it to see where it's cooler and it emits in the near infrared on Webb. We can also see those beautiful ionization front here on pillar 2 or the central pillar of it. And especially on the left side, you see these fingers of things that look a little bit like hair. And you got the same pattern in the near infrared as well as in the visible, and they're streaming off. And it's just, gorgeous structure. We also see a lot of ionization on the pillar 3, the dog pillar. And in particular, there are 2 outflows from it that you can see coming directly off of the pillar and streaming away. But if you look in detail, there's this ionization cloud here in the center. And it looks like this flow goes up and sort of turns a little left. Maybe the winds from the stars are pushing it to the left. So the ionization outflow flows away from it. And then it turns a little left. And it also looks like there is a ionization flow that comes away off the back of it and turns to the left as well. So you notice how dark the pillar 3 is here. All right, the dog pillar is. That means it's significantly backlit by the light of those stars, means there's an awful lot of ionization happening, and that could be producing these ionization flows. I have to say, I talked to an expert in the field, all right, and while I see this and then this sort of makes sense to me, she was like, well, sort of, maybe that's nice speculation, but there's no strong evidence for it. Whatever, there is a cloud of ionized gas between pillar 3 and pillar 2, the right pillar and the central pillar, right? And that was kind of confusing. And until I got this into my head, it was kind of confusing, especially when looking at the Webb image, because you can see in front of the central pillar, there's this sort of triangle of blue haze. And if you don't know that that is a ionization cloud existing between the pillars, you try to interpret it as being part of the pillar, and you get a wrong idea in your head, okay? So it's important to understand that there is a cloud of ionized gas in between these 2 pillars, all right? And that'll help you interpret the structures better. Okay. Let's go to one of the highlight points on the left pillar, a crown of fingers. So what I'm talking about is all of these small little fingers on the top of the left pillar. All right, and here are some arrows to draw your eyes. These are small dense regions, obviously. They're sort of like mini pillars, right? And they're dense regions that's resisting the erosion. The top of this pillar is being directly bombarded by the ionizing radiation, eating away things, but these are dense regions that are resisting it, okay? And so one of the postulations back in the 90s was that, okay, these mini pillars are solar system size. They're, thousands of astronomical units across, and maybe these could be individual stars in formation, right? And that we're seeing that the radiation is just pulling down to an individual star. Unfortunately, when looked at in X-rays with the Chandra X-ray Observatory, they did not find any protostars in these mini pillars, in these fingers. And if you look at the infrared light from Webb, we also don't see them. All right, so it doesn't look like that idea from the 90s is going to hold true, and that these are going to form stars. Matter of fact, looking at that infrared, if I were looking for protostars, all right, I might go where I see these red blotches here in these two places. But let's leave that for later because they'll both come up in a bit. Let's go to a real embedded protostar that we see in the central pillar. And we call the right pillar the dog pillar. We call the central pillar the Dementor pillar, okay? Because it looks like one of those Dementors from the Harry Potter films, right? And it's got this big, long thing. And it's all dark, except for up at the top, there is a red blotch. All right, and let's zoom in on it. And here's the Hubble and Webb images. The Hubble has this little red blotch. All right, and then up here at the top, it has another little red blotch with a white thing in it. And it's like, okay, there's, this is unusual because the rest of this Dementor pillar is all this nice dark brown with the yellow on the edge. So going to the infrared, we see similar things, but even more of it. All right, we see a bright white region going here. We see this red sort of linear feature working its way down the pillar to where it's we have the red blotch in the Hubble image. So the answer to what's going on here comes from a velocity map, okay? That if you're looking at this pillar and you take a map of the velocities in the area, they see in this velocity map, this blue splotch here, okay? That is blue shifted material. That is stuff that's flowing toward you. And you see that red splotch, which is red shifted material, stuff that's flowing away from you. And connecting them via a line, you get a jet. There is, at that white circle, an embedded protostar that has a jet streaming off of it. One jet coming towards us, one jet going away. So we see evidence of this embedded protostar and the jet from it in both the Hubble and the Webb image. And we can show that it's actually there by doing this velocity map. All right. And so we can actually detect stars that are forming inside these pillars. We also see an actual jet, all right? And we've seen this since the 1995 image, okay? This is over on the left pillar, just below the top. And you see this linear feature running through the center, okay? That is a jet that's going on there, all right? And jets are common in star-forming regions, okay? One of my favorite pictures that includes jet is what was called Mystic Mountain, released in 2010 from Hubble. All right, and you see right at the top of it, at the top of this little pillar, you see a jet and it's streaming out. And then over here, lower down, you also see a much longer jet, okay? And I like to call these jets sort of birth announcements of stars, okay? Because as the star is finishing its formation, it spews out these jets, okay? And those jets are evidence that there is a star in there. But what we don't have for Mystic Mountain, and we do have for the Pillars of Creation, is two epochs separated by 20 years. All right. So here I placed some arrows to guide your eye. This is the 1995 image, and this is the 2015 image. And I'm going to blink back and forth and sort of create a little bit of an animated GIF. And if you'll look really closely, you can see motion going on over the course of 20 years, right? So we can see the motion of this jet occur over the 20 years. We can also see it in that jet in the Webb near infrared. And it turns out this jet is moving at around 720,000 miles per hour. Okay, it's 200 kilometers per second in astronomical units, but that's 700 hundreds of thousands of miles per hour. Okay, and it's moving across the space in the nebula and measurable by Hubble over the course of 20 years. That's what you get when you have high resolution. However, all right, also I wanted to point out that this is that red dot in the near the top of the pillar in Webb, where I said, hey, you know, that red kind of indicates that we might have an embedded protostar there. Well, turns out there must be a star there because it's emitting a jet, and but we can't actually see the star. We can see the jet that tells us there's a newborn star there, but we can't see the star itself. Want to see some newborn stars? Yes, you do. Okay, let's go. All right, so this is a region lower down on the left pillar. All right, and here there are two pillars that lead out to what look like could be protostars. Okay, well, especially the one on the right. Okay, this, I thought of call this a smokestack, and there's something going on here that looks like that could be a newborn star right there. Turns out on the left side, you've got this pillar, this finger sticking out here, and you got this little star. And you go, could that be a newborn star? Yes, it could, because it's at the tip. But it looks kind of like this other star over here. And so how do we get know? Answer, of course, is what did Webb see? And with Webb, oh, yeah, this is a newborn star blazing at the end of this peak. And this is a newborn star at the top of the smokestack, okay? Meanwhile, this little star down here, if you look at Webb, nope, sorry, not a newborn star, okay? So at the ends of these peaks, some of these peaks, they do have newborn stars. Not at the top of the left pillar, but at the end of some of these peaks here. And it turns out it's even easier to see these newborn stars if you go to the mid-infrared from Webb. Yeah, bam! Okay, that is the newborn star just blazing out there. You get rid of most of all the other stars, and these newborn stars inside the pillars seem to pop out. Matter of fact, the Webb mid-infrared is the easiest way for me to find various newborn stars, evidence of them. We see them in the two that I just showed you. We see one in the middle of the central pillar. We see the newborn star at the top of the middle pillar, which was the embedded protostar that I showed you previously. We see two more up here near the top of it. This one is the one that I mentioned earlier that had that red glow in the near infrared and said, hey, that looks like that could be an embedded protostar. We actually see the star in the mid infrared. But what we don't see is the star here at the jet. We see the evidence with the jet, but it must be embedded so deeply that even in the mid infrared, we don't actually see the star. So that's kind of cool. All right, so that's my tour of the pillars to show you all the interesting science points we want to highlight. Let's take these pillars and pull them into 3D. All right, to do that, I'm going to use a paper by Anna McLeod and company, and they use the MUSE instrument on the Very Large Telescope at the European Southern Observatory. And this is what we call an integrated field unit, okay? So it takes images but it takes images across many wavelengths at the same time. Okay, so you have an image at 400 nanometers and then 500 nanometers and 600 nanometers and 700 nanometers and lots of nanometers in between. And you're able to actually get images and spectra at the same time in one observation. These are really cool instruments. And from that, you can look at the individual spectral lines. And from those spectral lines, you can derive motions, or the astronomical fancy word for it is kinematics. And you'll see kinematics in the title of this paper. So they were trying to not only understand the emissions from these pillars, but also their motions and such. So the basic idea of the pillars is that while it looks like three pillars in a two-dimensional image, it actually is four pillars, okay? So this left pillar, pillar 1, has a top half, pillar 1A, and a bottom part, pillar 1B. Whereas pillar 2 and pillar 3, the Dementor pillar and the dog pillar, are together. And the European Southern Observatory was really jazzed about this paper, and did a press release image of a 3D model. This sort of gives you a basic idea of how they're structured in 3D. Our team will improve on this in just a few minutes. All right, but what is going on here is in the paper, they're exploring various measures of the different pillars. And so this one is the extinction measurement, okay? So the deeper the pillar is inside the nebula, the more gas that's in front of it, okay? So if you've got a lot of gas in front of it, you have what's called a large extinction measure. And if you have less gas, you have a lower extinction measure. So they measured pillar 1A, pillar 2, and pillar 3. And they got this plot for the various pixels that they did this measurement on. And this purple represents pillar 1A, and you can see that it's got a higher extinction measure than this green, that's pillar 2, slightly lower pillar extinction measure, and that's even, but even lower is this red graph, which is pillar 3. So what does this tell us? That in our position, pillar 3 is in front of pillar 2, which is in front of pillar 1. They didn't measure pillar 1B, okay? So the pillars are actually ordered in distance from right to left. Another really useful figure in the paper are figures 16 and 20, where we're talking about the radial velocity. This is actually the figure where I pulled that velocity measurement for the embedded protostar. But here I'm just going to talk about the pillars themselves. All right, and in this color map plot over here, you can see that the pillars are sort of outlined in green, okay? Whereas the background is this yellowish red, okay? And that's important in that the pillars are at a different velocity than the background gas, okay? All right, so the background gas is the gas of the nebula. And that is actually this pink peak over here in the plot of figure 20, all right? Pillar 1A has a certain average velocity that's different from pillar 1B, that's different from pillar 2, and that's different from pillar 3. And in this table down here in the lower right, you can see the average velocities of these pillars. And so each pillar is a coherent cloud. Okay, each pillar is a coherent cloud. They are separate clouds, and they're actually moving at different velocities, so they're slowly separating and becoming farther apart. You can't really tell distance from velocities, but you can tell that they are moving different in a coherent manner. All right. So based upon information like this and lots of other information, you can go read the paper for yourself, they came up with a cartoon drawing of the three-dimensional structure. All right, so those three stars that I mentioned that are important. Oh, by the way, this represents the observer's eyeball, okay? So the observer is looking from the left into this image. All right, these are the three stars, the ionizing stars, the ones that are creating the big stellar winds and radiation that create the pillars. And this is their cartoon drawing of pillar 1A in the back, pillar 1B in front of that, pillar 2 in front of that, and pillar 3 in front of that. Okay, so based on that and about 10 or 12 other papers that I read on the Eagle Nebula and the Pillars of Creation and the star cluster NGC 6611, we set to work doing a visualization model, okay, and creating it in 3D. And I said we didn't want to do this until we could do it right. And this is the team that did it right, okay? These are the 9 of us on the visualization team here at SDSCI. And I cannot say enough good things about this. I get to be the front man. I get to explain all this to you, but these are the people that do the work, okay? All right, so let's start with those Hubble and Webb images of the pillars. And then we, boom, 2D image work, get rid of all the other stuff, leave behind just the pillars, and we actually separated into each of those 4 pillars, 1A, 1B, 2, and 3, okay? Then we've got to model them in 3D, and this is a slide given to me by one of our artists, and that starts with a block model and shapes it a little bit more, and just from the images, you can actually get the silhouette structure of it. But that's not good enough. We need the front back. We need to go know how do we structure it like that. So what we actually did is we put those 3 stars into our 3D model, okay? And we use them as light sources to shine onto the pillars as we sculpted them, right? And we ended up sculpting to get the model as lit when you light it with those stars to match the gold tones that are seen in the Hubble image, okay? So wherever the model is being hit by the light of those stars, that's where the ionization would happen, and these gold tones show you where that ionization has happened. Now, do we get a perfect match? No, okay? But do we know exactly where those stars are in 3D? No. Do we know exactly where the pillars are in 3D? No. We get a good enough match to try and come up with something that feels like and represents the science that's going on in the image. Other thing that's really cool is when you look at pillar 1B, all right? And on the left side, you see the Hubble view of it, and it's dark. Okay, so obviously pillar 1B, the front side isn't getting much light from those stars. It's the back side that is illuminated, okay? You only see a dark cloud. So let me ask you, why is the Webb image glowing? The light isn't hitting the front side, but the Webb image is glowing. And that's because with the Webb image, you're actually seeing the back side of this pillar, all right? So here's what's happening. It's really cool. All right, the light is hitting the backside of it and then warming up the dust so that it radiates in infrared. Now, whereas the pillar is optically thick in visible light, it's optically thin in infrared light. So the light is actually traversing through the pillar and being able to be seen in the front. So with Hubble, we're seeing the front of the pillar. With Webb, we're seeing the back of the pillar, and we can use that to sculpt pillar 1B. So here are the wireframes, and then the smooth shaded, and then the lit model, and finally the texture model of our 3D pillars. And then there is one other element that's really crucial to doing a good 3D model, and that is getting Anna McLeod to be your science advisor. She joined us for about 3 web video conferences where we brought up the 3D model that we were creating. We talked it through with the whole team and everything, and she was able to give us corrections, give us her views, or, you know, sometimes when we talk to these astronomers, they go, I don't know, I can't tell you you're wrong, but I can't tell you you're right. And it's like, okay, well, then we've made a reasonable scientific assumption here, or a scientific approximation. So using all of this and using all the work, we're able to get the scientist herself to come in and collaborate with us to creating this wonderful 3D model. Then we take these hard surface models and we want to turn it into dust with gas on top of it, okay? So this is the volumetric work, and we create a base density. We fill those pillars with particles, and we do more for the Hubble because it's denser for the Hubble, and less for the Webb because it is more transparent for the Webb. Okay, then we apply the images and drop it onto and give those particles color from the images of Hubble and Webb. All right, and that was actually not as easy as it sounds. It sounds like you're just applying it, but you got to actually get the surface of it and wrap around because the camera is not going to stay just in front. It's going to pull around, and so we had to do an awful lot of work to try and get this to work and feel right as we brought the camera into its various positions. And then we have to pull an ionization wind off of it, okay? So we use those lightings, and wherever the lighting hit it, we then created ionization fronts to come off of it, okay? And you remember I mentioned that it kind of looks like hair? Well, that's actually how we modeled it. We used the Hollywood technique for creating hair on animals to create the ionization flows on the pillars. And what's really great about that is they have the tools to be able to like trim the hair and make it longer here and shorter there. And we're able to art direct the ionization wind coming off these pillars. Yes, that was great. We also used several other effects, including more tiny little hairs and other glows to fill in the other stuff that's working around it. And so here is a breakout of some of these different layers that we would put into sculpting the pillar, to modeling the pillars in the volume. All right. Then we have to do the rendering, okay? And so we've got the Hubble model and the Webb model. We've got 4 pillars in each model. We've got 4 or 5 render nodes for each pillar, and each render node contains a beauty, emissive color, and lighting pass, okay? So it's a huge render process. And why do we do this to ourselves? Well, because by having all these separate components provides much more precise control in getting the look and feel right when you are compositing them together, when you're sandwiching them all together. This plot over here doesn't make much sense to you, but let me just tell you, it was a huge render job. 3 or 4 weeks of rendering on a render farm. Actually, they built us a render farm and we broke it. And then they built us a bigger render farm and we still pushed that to its max. And then we ran renders on workstations all around our department. It was a huge, huge job. It was the largest render our team has ever done. And that's saying something because we've done IMAX films, okay? So this was really big. The next stage, of course, is compositing, taking all of that together. 31 passes for the Hubble model, 27 passes for the Webb model. These are the compositing trees in our software, and everything flows through them. And then you got a roto, and you got to do all. It's just much bigger compositing job than we've done before as well. All right, finally, we're getting to the movie. But got to give a nod to the sponsor. Our people who paid for all of this is NASA's Universe of Learning. This is a collaboration amongst 4 institutions for showing the public the fruits of NASA's efforts. And I run the AstroViz project within NASA's Universe of Learning. And we do these multi-wavelength visualizations using visible, infrared, X-ray to give you a 3-dimensional structure to these 2-dimensional images and to give you information. We got to have learning messages about all these things. So what was going to be the message for this project? Well, it's the interplay of stars and dust. The stuff I mentioned at the very beginning when I was talking about the Milky Way, how we have stars and dust and gas, and how do they work together to create the pillars of creation, but also in the general process of star formation. So with all of that as precursor, we have a 4.5-minute film for you to play for you. And I hope, even if you've seen it before, it makes a lot more sense to you now that you have the science background behind it. Please enjoy.
The luminous band of our Milky Way galaxy stretches across the night sky. It is a contrasting combination of bright starlight and dark dust lanes. Stars along the pancake-like disk are seen in short-wavelength infrared light, while long-wavelength infrared light features the dense dust clouds. These dark dust clouds are places where new stars can form. Newborn hot stars heat the dust clouds, and their cores glow brightly. The Eagle Nebula is the birthplace of a cluster of luminous young stars. Infrared light can trace the dusty skeleton of the nebula. And X-ray observations reveal over 1,000 stars in the central cluster. The largest stars in the cluster emit strong stellar winds and energetic radiation, which stream across the nebula and shape the iconic Pillars of Creation. Made famous by the Hubble Space Telescope using visible light, the pillars are equally amazing in the infrared view of the Webb Space Telescope. Examining their structure in 3 dimensions, they separate into individual clouds. The right pillar is closest and is backlit by the star's intense radiation. Glowing ionized gas streams away from the pillars. The infrared view of the central pillar reveals vibrant evidence of an embedded protostar. The top of the left pillar is directly bombarded by energetic starlight. Dense pockets of dust resist the erosion and create narrow, finger-like peaks. Lower down, jets from a newborn star shoot away from a peak. The semi-transparent body of the pillar lies in the shadow of the dense top. A newborn star blazes at the end of this peak, underscoring the nickname, Pillars of Creation. Stars form in these dusty pillars. The dusty pillars are shaped by emissions from young stars. The young stars form within giant dust clouds. Dust clouds and stars are strewn across the plane of our galaxy. The interplay of stars and dust creates cosmic structures on many scales.
Okay. All right. And there is a bonus product from this. We took our 3D model that we used for the visualization. We turned it into an STL file format, and you can download that and print that on a 3D printer. And here is a printout of one, and then you can examine it and look at that structure in 3D interactively. All right, I invite you to explore more. The videos are on youtube.com, Hubble Space Telescope. We have an astronomy visualizations playlist with, I don't know, 50, 60 visualizations available for you. We also have a large number of resources related to the pillars of creation and to star formation from the Universe of Learning at universeoflearning.org. You can also get the 3D printable model there or on Hubble site or webtelescope.org. I hope you enjoyed my talk. I really hope you enjoyed the visualization. My whole team had a blast creating it. This is what we really love doing, these big projects that come together. And so far, the reaction has been absolutely amazing since it was released last week. Thank you for listening. All right, so I'm going to stop. I stopped my screen share. Grant, will you turn on your video? I have not looked at all at the YouTube chat, so I have no idea what's gone on there. Do we have some questions in the chat or comments that I should that people would like me to address?
Absolutely. We've got quite a few, and I'm going to keep an eye on a couple more coming in. Most of the comments so far have been variations of how incredible the work is and how much has gone into it. So
yeah, that's one of the things that people don't recognize. They see, oh, this is just, computer graphics. They're artists just doing things. No, no, no. This is all based on science as much as possible. And when we show them, it's like, wow, didn't realize you had to do so much to do these pretty pictures, right? So thank you, folks, for appreciating that, the hard work of the team that goes into it.
There is a big difference between an artist's concept and a visualization in the terms of what,
at least as we define it.
Yes. Okay, so a returning viewer wants you to talk a little bit more about the Milky Way image that you first put up when you started the talk.
Is he talking about the simulation? Or
yeah.
Okay. So the simulation was done by a group out of Caltech.
Okay.
And they call them the FIRE simulations. And I used to know what FIRE stood for. But basically, it was a Milky Way analog. Okay. They put together a whole series of simulations. And this one, they actually collapse the galaxies and do things with them in order to study the physics of Milky Way type galaxies. And this was the one that the folks there said, okay, this is the most like the Milky Way in the Milky Way structure. And they put their data online for me to download. And then I was able to visualize it and make it feel like the galaxy. And I just absolutely love that when I was able to spin it like that and see the edge on versus the face on, and they both views looked great. I was like, best simulation data I've ever worked with on that.
Everything's cool until you move the perspective and it all just...
Exactly. I mean, I've never been able to take a galaxy and spin it sideways and have it just naturally show me the dust lanes very like that and everything. And that was a fun thing. Can't remember how many years ago I did that one, but it was just great to be able to show people the pancake structure of the Milky Way.
So related, but not something that you may necessarily be able to answer, but you can at least answer for yourself. When you create these sort of 3D images or these 3D constructs, do you interpolate stars that you can't necessarily see? Do you balance everything so that it has a similar brightness scale? Like how are those sorts of decisions made? Is it... Well, I'll just let you talk.
Okay. So we cannot go for scientific accuracy, okay? If we were trying to do scientifically accurate 3D models, we'd be doing research level work, okay? Stuff that would get published in the Astrophysical Journal, all right? What we're doing is we're taking these published papers and we're interpreting them into a reasonable approximation. So I like to say that my goal is to be scientifically reasonable, okay? I want to be able to show this to any astronomer anywhere and have them go, okay, that's a reasonable interpretation of it. Are we exact? No, we can't get exact. I think if you watch the sequence and you see those fingers at the top of the left pillar, they're not as tight and dense as they should be compared to the images, right? But using our volumetric technique, we couldn't model things on that small scale without using so many particles that it would become prohibitive in terms of render times and everything. So yes, we do interpolate. What I like to say is we use scientific knowledge when it's available. We use scientific intuition to extend that. And then when, as I said, the experts say, well, I can't tell you you're right, I can't tell you you're wrong, that allows us to use a little bit of scientific artistic expression. Okay, it's all science guided. I mean, I used to say, oh, then we use artistic license. No, we don't actually use artistic license because it's scientifically guided artistic license. Okay, so it has to pass the astronomer, me being the astronomer and the director of it. I get to say, hey, that doesn't feel right to me. Let's change it like this. Okay, and that's one of the things. One of the artists who's just started with us last fall. One of his comments the other day was that we were doing another group chat on Zoom or something like that, and what his comment was, trying to be science accurate in creating these graphics is brand new for him. Okay, because most of the time when you're creating things for commercial environments, if it looks good, it is good. Now, that's not true here, okay? You can make some really beautiful stuff that's scientifically crap. You see it sometimes in these movies, unfortunately. But the beauty is only on the end part, okay? We have to get it right and then make it beautiful, okay? Or we're trying to do both at the same time. Actually, that brings up a quote that I like to say, that it's the knowledge that there is truth behind that beauty that gives our visualizations their significant power.
Yeah, you are trying to convey something first and be a pleasing visual as a secondary. Yeah,
Yep.
I like that a lot. It's a good quote. Okay, so let's go on to the next one. What kind of, and I know these are your favorite questions, I'm throwing one at you anyway. What kind of scale are we talking about with each individual pillar? Because we've seen them flat on, but that doesn't necessarily give us a concept of how large they are in an actual space.
Okay, so the total length of the left pillar from pillar 1A to the bottom of pillar 1B is about 3 light years. Okay, and so to give you a scale on that, it's 4 light years to the nearest star from the sun, right? So this is a dense region of stuff for these dust pillars. So you're talking in terms of light years, and basically the front to back scale is several light years. Okay, the scale of these star forming regions, I said Orion was like 10. I think it's like 14 actually light years across or something like that. Or maybe that's the Crab Nebula. Can't keep everything in my head. So you're talking tens of light years for the scale of the star forming region. Okay, and so this one's thousands of light years away. But if you take that scale into effect, just a couple light years in terms of the scale here.
Awesome. All right. Other than giving the public an appreciation of the data and of the bodies themselves, how are these models beneficial to doing actual science?
These models are not intended for writing papers on, okay? We're actually taking the papers and interpreting them into an artistic, a scientifically guided artistic model. How about we'll call it that? We do, however, find that by pulling them into 3 dimensions, we help astronomers who sometimes don't have really good 3-dimensional visualization skills in their brain, because that's not something we taught in graduate school, understand the structure and be able to guide their intuition when they interpret things. So, for example, I talked about that ionization cloud between pillar 3 and pillar 2, right? And how it looks to me, because I do 3D viz all the time, like, yeah, it kind of looks like it's flowing off there. Maybe somebody will be able to go and actually measure that and tell me whether I'm correct, or hey, Frank, you're full of crap. Okay, sorry. I freely admit that I was speculating there. But that's the kind of thing that you need to do in science, is to observe very closely. And I gotta tell you, as evidenced by my talk, I've looked at these images really, really
Very
closely
closely.
for many months, and then make a hypothesis and then go test that hypothesis. All right. I don't think I have a strong effect on things, but the person asking it is correct. Helping people to create those mental models of the 3D structure of these various objects is our primary purpose, right? When an astronomer comes to me and tells me, hey, I love that visualization you did, I use it in my class all the time, that really warms my heart, because if I can be shown to, if I can get the visualizations in front of students, then they can start to imagine, they can interpret these two-dimensional images. But I gotta say, that same stuff does work on astronomers as well, even though it's aimed more at the public and lifelong learners.
Yeah, absolutely. I mean, having a visualization is a learning tool regardless of how it is applied. Some
Right.
people
And it's amazing the number of my friends that have said, I never knew that they were separate. It looked like it was just one, all three pillars were connected. And to my astronomer brain, that was never even an issue. Of course, they're separate pillars. Now, pillar 1 being two separate pillars, I didn't know until I started this project. But and it's just like, right. If you're just interpreting it on the basic things, these pillars look like they're all connected. They're all just one formation, like a mountain ridge, right? But they're not. They're actually these isolated things. And so that fundamental understanding is really important.
There were at least 5 or 6 comments between people talking about just that. Is when you take it as it's original, it's almost like a painting, like a still image. It's all together, but in reality, they're so very distant. It's very close in astronomical terms, very distant in human terms.
Yes. And did somebody ask how fast is the spaceship flying? That is it flat? Is the camera moving?
Not in here, but on YouTube, yes, they did.
People always ask that. Okay. Yes, it's many times the speed of light. Okay. Many, many times the speed of light. I haven't calculated the actual one here.
Let me grab another question here. Oh, what is the actual composition of the pillars?
Okay.
We can see, like, the ejecta, we can see you talked a little bit about the ionization in it, but what is the actual composition of the structures themselves?
Okay. So the pillars are dust. Okay. They're going to be cold molecular hydrogen and mixture of other molecules and everything. And building those molecules into bigger particles, which we call dust. We often say gas and dust so often in astronomy that there's a temptation to say, oh, these are gas and dust. But these are really just all dust, except for the gas that's being created from the ionization fronts. Okay. Now, the whole nebula is gas because those stars have ionized the hydrogen. And so ionized gas within the nebula. So in between in between the pillars and surrounding them is all this ionized gas, but most of that is not glowing like the ionization fronts. Okay, that cools off. That ionization fronts is barely hot, and then it cools off to being, about I don't know, about 10,000 degrees of things. So we see the stuff that's ionizing away brighter than we see the background gas, but. Yeah, the pillars are just dust clouds.
All right. When you're talking about newborn stars, quote unquote,
Yes.
how old relative are those stars?
Okay, so a newborn star, this may sound strange, is probably anything up to about 1 million or 2 million years old. Okay. Stars go through various stages. Obviously, they go through an X-ray emitting stage that I didn't appreciate before this project. And it appears that a lot of the jet emission occurs around 100,000, few 100,000 years after the ignition. Okay, so the birth of a star is the fusion ignition in the core. Okay, when you get hydrogen fusion in the core, that's the birth of a star. Okay, that's the power source of the star. But the star continues to form after that, and these jets that spew out, okay, are in hundreds of thousands of years, and then you get rid of those, and you're still producing these huge stellar winds and the high energy radiation. And so, like the stars in Orion are about 2 million years old. Okay, the stars of the NGC 6611 cluster, I think they're like 1.5 million years old. The ones that are in the pillars, however, are really young. You can see the jets, so they're probably, hundreds of thousands of years old. It's really hard to age date stars, and I'm not an expert at that. So those are my guesses.
Fair, but given knowing what to look for is, I think, a solid answer to the question.
Yeah.
Uh,
I got to say, there was a Webb press release on Serpens the other day
yes.
that showed those beautiful jets. Those stars are estimated to be about 100,000 years old. Okay. And they had the aligned jets and everything. It was just really wonderful. Great image. I should have done that for the news from the universe today, but didn't have time.
It's all good. We can either do it next month or chat if you want to.
We'll get it next month if Maka doesn't cover it in her talk.
Fair.
It's going to be really hard next month because she's going to go through all the JWST highlights. And I'm like, okay, let me just. Can I
But
see
what do I talk about?
So I don't step on your results.
So for chat, yes, there's a Serpens release. It's on Webb Telescope. Highly recommend to go check it out. It goes a little more into detail about that if you want to see what a young star is supposed to look like. Okay, so we'll make this the last question unless you've got anything.
That sounds good.
Okay. Are any of the 3D reconstructions available in a model format that can be manipulated by someone outside of us? Maybe like via a browser or something similar?
We have released the STL version, and I'm sure the STL came out of an OBJ. So you could probably take the STL back to an OBJ and then import that into a 3D modeling software. We don't release our models because it's an awful lot of work to support them and such, and to do that transformation. And the team that works with me is very busy on all the various Hubble and Webb press releases and everything. We barely have time to archive what we've done on our own project, much less support other projects. We do get a request for this. I'm going to the International Planetarium Society conference in Berlin this month, and they're going to ask me the same thing. And so, yes, you aren't the only one wondering, hey, can I get a hold of your models and then play with them my own way? The hard surface models could possibly be available, but I mean, we sort of made that available as SDL. But the volumetric stuff is way too complicated to do. I mean, and so we said we got 58 different passes that we did for the volumetric model and such. So yeah, we don't want to take the time to try and share that with the world.
What are some resources that they could use, though?
Okay. In terms of, I know that there was a really good model, a hard surface model created by Luis Calzada for the BBC documentary. I don't know if he has released his. I wouldn't expect so, but he's an artist at the European Space Agency. And so they flew into the top of the Hubble pillar.
Yeah.
He actually did the fingers really well, but he did mostly a hard surface model. He didn't get the volumetrics in there. But I really big thumbs up for Luis and his work there. Um, and so, there are ways to work off of that. But I really, in terms of stuff that's coming from us, the STL file, turn that into an OBJ. OBJ is the best I can do for now. We'll see whether the folks at the Planetarium Conference are able to twist my arm even harder than they already do.
Fingers crossed for you.
It's the first question anytime I give a talk in front of a planetary audience. Is one, can we have your models? Two, actually, one, is this available in a dome version? And two, can we have the models? And it's very hard to create dome versions because you not only see what's in front of you, you got to fill out what's behind you. Okay, and we modeled the fronts of the pillars and around the sides of the pillars. The backs of the pillars are significantly unknown. Okay. And even Anna McLeod didn't really want to speculate too heavily on what the backs of the pillars look like. So in creating the camera move, I stayed away from showing the backs of the pillars too much, just so that I kept with the desires of my scientific advisor and such. And also, my artists didn't want to, once I've got a camera move down, they're going to create structures that are seen by the camera, and the structures that aren't seen by the camera, not going to worry too much about it. I mean, if you're doing a stage play, you don't build the back of the building on stage. You only build the front of it, right? Because nobody's going to see the back, right? Well, same thing here.
It also helps that we can't see the back. So then we get back into our discussion of, is it a visualization or is it an artist rendition?
How much extrapolation is too much extrapolation?
Yeah. It's a slippery slope, but worth talking about for sure.
Absolutely. All right. So that's our questions. Yeah, we're getting to 9:30, so let's cut off the questions there. All right. Thank you, Grant. Thank you, everybody else, for watching tonight. Next month, as I said, Macarena Garcia Morin will be talking about year 2, the updates of the exciting science highlights from the second year of the James Webb Space Telescope. Thank you for joining us tonight, and we'll see you then.